All right. So yeah, I'd like to ask you about your backgrounds. How did you get to where you are, and why are you so interested in the measurement problem? What got you interested in the measurement problem?
Oh, um, hmm.
Ooh.
Do you
Okay,
want to go
so
first?
well, we can just start first. How did you end up where you are? What's sort of your academic path?
Right.
Can you start with that?
Yeah. Should Nick, you want to go first or sure?
Yeah, you start.
Sure. Yes, I think I was sort of very interested in math in like school and like middle school and so on. And I was quite lucky that I actually have an aunt who's a math professor. And it was great because she introduced me to like stuff like linear algebra when I was 12, but in a very accessible way, really, really accessible way. And then eventually I discovered these Feynman lectures in physics, which is great because I skipped the first 2 volumes and went to the third, which is about quantum mechanics because it sounded cool. I didn't know much about it back then. But it was really nice that he kind of builds it up in a very, what now we would call in quantum information, operational way. So he starts precisely with this Stern-Gerlach experiment that you mentioned, James. And then sort of really from there, like talking about physically what we would expect, builds up somehow the mathematical structure of quantum theory, which turns out, for me, this is very surprising, that is basically linear algebra. And then this kind of led me to sort of, eventually getting very interested in quantum theory and stuff like Bell's theorem. And I think my mind was really blown the first time I saw Bell's theorem, which was really, I'm sure like anyone who first encounters Bell's theorem, it's really something that has an impact on you, right? And I guess with this whole sort of quantum information kind of way of looking at things, which is of course still consistent with the usual textbook quantum theory, but the focus again more shifts rather than looking at sort of, typically we start with like wave functions and these sort of mathematical objects as being somehow the basic things, and you build up to what we observe. With quantum information, often we say, okay, what we observe are probabilities, and we can see pointers on our devices pointing at various things, and we can make choices and so on. And we want to work backwards just to try to understand how we could explain what we observe in terms of quantum theory or in other theory. And I guess this way of looking at things gives a very nice correspondence between very fundamental things like Bell's theorem, which is really telling us something about the fundamental nature of reality, but as well as to, concrete like games that you could play. And you could say that, well, the CSH inequality is really just a bound on the maximum winning probability in a simple game. And I could never win this game with higher than that probability if I was working in classical theory, but quantum theory gives me a way to win this game. And then this can allow me to do, say, cryptography and, encode information in a way that cannot be extracted by an eavesdropper and so on. And somehow this correspondence was something that really drew me into quantum information. And maybe the measurement problem itself is something that comes from just looking, I guess, at, in a way, just looking at quantum theory a bit more carefully, like this. Like as I said, for me, it's kind of really interesting, this apparent tension between these two kind of postulates, right? Like the unitary evolution and this sort of probabilistic description that you get from the Bond rule. And I think somehow something that ties this whole study of the measurement problem as well as Bell's theorem and so on together, I think, is this idea of causality, right? Like somehow it's central to these when we talk about, relativistic relativity theory, it's really what's at the core of it is the idea that causal influences don't go outside the light bulb. This features very prominently in the Bell's theorem, but also it's something that we have to care about when we think of the measurement problem as all these. So that's somehow the summary of how I ended up where I am. But maybe on a more concrete level, I studied in India for my undergrad. And then I sort of did my master's at ETH Zurich, which because the group here of Renato Renner, they work both on these sort of foundational things, but also like quantum cryptography and more applied side of quantum information, which I was both interested in. And I moved to University of York in UK for my PhD, and now I'm back with a grant to do my postdoc at ETH. So that's where I've been.
Okay, excellent. And Nick, Can you beat that?
No, probably not. So I guess when I was quite young, I definitely didn't expect that I would end up doing anything like physics, because when I was a kid, when I was like 12 years old or something like that, I sort of thought that science and math was kind of boring and stale and not very creative and so on. And I thought it'd be much more exciting to do something like study like philosophy or even literature or something like that. But then my perspective on that completely changed, I guess, when I was about maybe 16. My aunt got me for Christmas Einstein's book, his sort of popular science book, where he explained relativity theory. Well, I say popular science, but he explains it in quite a bit of detail. It's quite good. And I remember reading that and thinking, wow, this is portraying a vision of the world that's so deeply counterintuitive, so unnatural, and yet kind of beautiful and graspable. But you know, it's not just conjecture; it's actually confirmed. This is it's backed up by experiment. You know, science has given us a really good reason to believe that the world is very different to how we would naturally expect it to be. And I just found that central fact like so ridiculously cool that I just felt like I kind of wanted to pursue it. Then I thought I'd do just physics at university, but I was quite lucky because I had this good philosophy teacher who encouraged me to actually do a joint honors thing. So I ended up doing 50%, 50-50 physics and philosophy at Bristol, which is a course that I would really, really recommend to people. Like, it was great because the two complement each other so well. So I mean, actually in the first couple of years, we weren't doing a lot of quantum theory and we weren't really doing philosophy of physics. And towards the end of the first couple of years, there was a point where I actually became a little bit disillusioned because, you know, a second ago, I said the reason why I got into the whole idea of physics was that we can have a good reason to believe that the world is very different to how we expect it to be, which is a very attractive idea. But in philosophy, my enthusiasm for this momentarily got kind of crushed by something called the underdetermination problem that philosophers study, which says that in principle, you could imagine that two theories that portray the world in very different ways could in principle give rise to exactly the same empirical predictions, which means that we can't actually tell just from what we observe what the world is like. And so, yeah, Einstein said that, you know, space-time is curved and that's what explains gravity, but you can come up with a theory that says that space-time is flat and it explains the same phenomena via these forces in a flat space-time in a way that's a bit more analogous to the old Newtonian theory. And so I read about that and I thought, oh God, maybe it all doesn't work out in the way that I hoped it would. But then I guess that maybe somewhat the same with Vilasini. What changed that for me was Bell's theorem. This wonderful idea of a no-go theorem that you can make. It's such a simple idea. You just make a series of assumptions. You assume X, Y, Z, and together you derive a contradiction. And then unless you want to be somebody who believes in contradictions, you are not allowed to believe that all three of those claims are true. And it doesn't tell you which one of those three claims are false, but it does tell you that one of them is false. So you at least know something. And then that really reignited my enthusiasm in a big way. It filled me with this sense of optimism that really we can at least learn something, even if that something is of a negative form, even if we're just learning what sets of principles we can't all believe at the same time. And then when I started my PhD doing quantum foundations with John Barrett, who's a very, very good supervisor, then at some point in the first year or the second year maybe, then I finally came across these measurement no-go theorems. And I'd learned about the measurement problem, but in philosophy classes, which I suppose hadn't fully caught up to the recent developments in the foundations literature. But my God, I found this amazing because what I was already used to in the context of Bell, I now saw in the context of the measurement problem, that we could state in a rigorous way that we could understand the measurement problem as the statement that a series of assumptions together imply this contradiction. And so we really get to learn something about the world. But with Bell, what we learn about the world, in my view, is that it's non-local. But what we're learning about the world in the case of the measurement problem is potentially if you could imagine such a thing, far more exciting and interesting than the idea that particles somehow influence each other or know each other at a distance. The idea that observed events are not absolute, the idea that there's not a unique or definite fact about you seeing something like a light bulb flashing or it raining outside your window or somebody dropping their pen, the idea that there's not unique and definite facts about that is way more, I think, crazy and difficult to get your head around than the idea that there's no non-locality in the universe. And so for me, I've always just been completely, completely floored by that. So yeah, in a phrase, I guess, like Vilasini, it's no-go theorems. No-go theorems are what's really got me excited about physics.
All right, excellent. Well, I think everybody will get really interested in the podcast by hearing about that. They're very, very nice. So it's no-go theorems. And there's a no-go theorem in the podcast, so everybody's going to love. Everybody's going to love. It works perfectly. It works perfectly. That doesn't always happen. So thank you very much once again for coming on the podcast. It was great having you on. I think everybody's going to love it. It was a really good conversation. I'm sure both of you were thinking that it wasn't, because good conversation is what? It's when you speak at least 2/3 of the time, and so only one person gets a good conversation. But I think, I was a lot worried because I don't do two people at the same time. I usually just have one person. I was a lot worried that it would be a lot more difficult to keep things fairly even, but you seem to work really well together. So that was really good.